Okay, so section 5.6, definite integral substitutions in the area between the curves. So this theorem number 7 is the same theorem in a way, and I say in a way because part of it is taken from the previous section. It's the same section as theorem number 7 that talks about the substitution rule for evaluating or solving indefinite integrals. In the previous section, I told you several times that indefinite integrals means when you don't have any lower or upper limit on the integral. You don't have this value a, you don't have this value b. So every time you have to be adding a plus c at the end, right? What was the process? You were given a function times another function. Specifically, the first one was a composite function. There was a function inside of another one, and it was being multiplied times the derivative of the inside function. Well, now, in this section, we're going to do definite integrals. We are going to have a lower and upper limit, definitely, but the way to solve this, at some point, is going to use the substitution rule as well. But the limits are going to have to be transformed. Your limits are not going to be the original limits given to you. They're going to be g of b, g of a. What's the g? The inside function. So you're going to substitute, or you're going to evaluate g at b, and that's the answer this is going to be. That's the new upper limit. G of a is going to be the new lower limit. And then you're still going to use the substitution rule, and you're going to change all this in terms of u. Okay, anyway. So we will do this problem in two ways. One way is going to be the old way. So this is method 1. I'm going to call it like that. And this is the old way. The old way was evaluating. Let me put probably an equal sign here. What was the old way in section? When I say the old way, I mean what you were doing in the previous section. Evaluating an indefinite integral. What does that mean? That the characteristic was that we didn't have any lower or upper limit. So there's going to be basically three things you're going to do. So three, let me see, transform the integral, evaluated. Yes. So you're going to do first, transform the integral. What does it mean, transform the integral? In terms of use. By using what? By using the substitution rule that you already know. Then you're going to transform the limits. Okay. And once you have transformed the integral, transform the limits. Sorry about all this. Let me erase, I forgot this was here. And once you've done all that, then the third step is going to be doing the actual integration. Integrate. So, okay. These two steps, you could do any of them first. Okay. Doesn't matter. As a matter of fact, you kind of do this two simultaneously at the same time. Okay. So first step is probably going to be as the old way. What's going to be u? Who's going to be u? U has to be the inside of another function. So the x to the third plus 1 is probably going to be our inside. The derivative of this is going to be 3x squared with respect to x. So we have to say dx. Now, that was part of number 1, transforming this integral in terms of use, which I'm going to do eventually right now. But at the same time, let's do number 2. Let's kill two birds with one stone. So let's transform the limits. How are you going to, what do I mean by transforming the limits? It's not going to be a through b. It's not going to be negative 1 through 1 anymore. It's going to be g of a through g of b. So g of negative 1 through g of 1. You may be wondering right now, what's going to be my g? Yes, this is u. But here u is the same thing as g of x. Where am I getting that? Because g of x here in the theorem is the inside function of another one. Here the inside of this square root function is x to the third plus 1. So besides I'm calling this one to be u on purpose to use the substitution rule, this is also g of x because that's the one inside of the other one. And that's how the theorem calls it. So then to do number 2, so with this I'm starting to do number 1, right? Number 2, what I'm going to do is I'm going to say, okay, well, the only way to transform the limits is going to be by substituting these two numbers, -1 and 1, into this, obviously one at a time. So then when, we're going to say, when x is -1, let's start by the lower limit, u is going to be -1 to the third power plus 1. So this I'm substituting it into u. Why into u? Because we said that u is the g of x here, and that's where you're substituting a and b to transform these limits. So this is going to be a -1 still plus 1 when you raise it to the third power, so this is 0. This is going to be your new lower limit, or transformed, right? Lower limit. When x is a 1, that was the upper limit, what used to be the old upper limit. Then u is going to be 1 to the third plus 1, which is 1 plus 1, which is 2. This is going to be my new upper limit. So now I'm ready to put together step 1 and 2 here. So it's going to be rewriting this. So you see how this square root of x to the third plus 1 can be replaced by x, the square root of u, and 3x squared dx is actually my du. So for you to see that, I'm going to rewrite this as the square root of 3x squared plus 1 first, and then I'm going to send over until the end this 3x squared. That's all I'm going to do. 3 times 3x squared dx. What are going to be my new limit and upper limit? It's going to be this number and this number. Lower limit goes at the bottom, upper limit goes at the top. That kind of makes sense, kind of logic. So I'm not going to use the old limits anymore because I'm trying to rewrite everything in terms of use and use the transform limits that this theorem is telling me to use. So then now change also everything in terms of use. So this is going to be the square root of u times du. All this is du. Remember, that was the derivative of the inside, and that's right here. I put in pink the things that I changed, the transform limits, and I transformed the integral. Now what's the third step? The third step is going to be integrate this. So how do I integrate it? I'm going to say, okay, so put a bracket here. The integration of this, you know, is u raised to the 1/2. So at this point, this is just rewritten. Plus 1 over 1/2 plus 1. You don't need the du anymore. You may close this, and you're going to put from 0 to 2. You don't need to put plus b, plus the letter c. That you only do in indefinite integrals when you don't have limits, but here I do. It's just that I transform them. So then I'm going to be saying u raised to the 3/2 over 3/2, and then the next step is where I would probably try to do the evaluation if there is not something else to simplify. What else can I do as far as basic algebra? I also see that I can do the following. I can create a fraction here. I have a 1 in front of the u, that's the coefficient of u, 1 over 1. So I do 1 times 2, which is going to be 2. and then I do 1 times 3, which is going to be 3, u raised to the 3 halves. This evaluated from 0 to 2. Final answer would be the actual substitution, 2/3 times, first we always put in the upper limit, the bigger number, raised to the 3 halves, minus 2/3, and instead of u, we put a 0, raised to the 3 halves, and then let's see what tricks we can do from basic algebra to simplify this. 2/3 times, why don't we rewrite this as the square root of 2 to the 3rd power minus 2/3 of the square root of 0 to the 3rd power. So I guess we can all agree already that 0 to the 3rd is going to be 0. Square root of 0 is 0. And 0 times 2/3, all this is just going to be killed because it's 0. So there's no minus anything anymore. So then 2/3, it's all I'm left with, times this. So 2 to the 3rd is going to be 8. Something that I can do, and that's basic algebra. It's, I know 8 doesn't have a perfect square root, but I know that I can write it as 2 times 4 or 4 times 2. That's the same thing as 8. This is simplifying the radical. And then times the square root of 2 times the square root of 4. And that would be 2/3. There's nothing I can do about the square root of 2, but the square root of 4, it's the actual, it's 2 actually. So then these are just simple numbers, simple coefficients that I could multiply together. Okay, those two. So then it's going to be, imagine you put a 1 under this one, even though that is not, and you do 2 times 2 is 4, 3 times 1 is 3, and you leave the square root of 2 to the side, or another way of writing this could be 4 square root of 2 over 3. Same thing. Both are correct answers. This is the area under the curve, which this in the calculator is decimals if you want to put it on the calculator. I mean, I don't know if the answer is going to be asked like that, but if you're like that, this doesn't make sense to me. How much is the area? Well, the area is 1.9, let's say, in decimals. Now, do you really need to write it as 1.9? Depends. If you're doing a multiple choice test, as you know, our tests are like that, then probably, but if not, that's fine. So, okay, this is using the old method. Okay. Just basically taking off I forgot what I wanted to say. Transforming. I'm sorry, not taking off. Transforming two things. Transforming the upper and lower limit. Transforming the actual integrand. The integrand is the expression you're integrating in terms of use, and then just using the new upper and lower limit, rewriting everything in terms of u, and then doing the integration, and that's your answer. So this is a combination of the old method, you're still using the substitution rule, and then also using this new part of the theorem of transforming this. Okay. So the old way was evaluating an indefinite integral. So at some point you remove the limits, but then you're not really removing them, you're just transforming them. So then the way we're going to be doing these problems now. We're going to be using this theorem at least in the first 4 problems. In the first 3 problems, sorry. This one and 2 more, we're going to practice doing the same thing. So then, next slide has these 2 problems. We're going to use the same steps. First and second step, you see, they kind of go together. You're going to rewrite this integral in terms of use, That's what it says. Use the method of transforming the limits of integration. And then you're going to transform the limits as well. So I guess let's start by saying, okay, who's going to be u, who's going to be what? So u, remember that u has to be a function that you see there, and then you have to also be able to see there the derivative of another function. If it's not there, you have to compensate for that. But why don't we say u is going to be the cotangent theta? This one's going to be like the first function. Now, where's the derivative of that function? Well, the derivative of cotangent, not the derivative, I'm sorry, the antiderivative of cotangent, it's actually negative cosecant squared. Where can you get this information again if you do not remember? All you have to do is, and it's negative cosecant squared theta, d theta, because you're integrating with respect to, you're deriving with respect to theta. You can find this, again, I go back to section 4.8 from the textbook, or the, I don't have a textbook, the ebook. If you go here, and I'm going to go back again to show you, section 4.8. That's that. Okay, let's go to the page where that is, here. So where it's the derivative of cotangent is, where is it? Here, is it here? Oh, I missed to put something. I'm just realizing. No, I did put it. Okay, because we are doing here, we're finding the derivative, not the integral. Sorry, I was looking in the integral formulas. These are the antiderivative formulas. So I want to derive, right? So this is not in this section. It's in a previous section, in another chapter, where we started seeing derivatives. So chapter 3. And we want to know the derivative, probably would be here. I don't recall quite well, but let's see here. Yeah, I think it has to be here towards the end. This is inverse trigonometric functions. It wasn't there. 3.9. Section 3.9, so I go here. That's not it. Keep going forward. I think it was that page. No, that's design inverse. 3.8. Oh, this is inverse derivative of inverse functions. No. Derivatives of trigonometric functions. Oh, finally, 3.5. Here, okay, so yeah, 3.5. Section 3.5, if you want to go over where am I getting these formulas from, I think there's a summary at the end here in this section. Here. So, what's the derivative of cotangent? And you can find it right here. It's negative cosecant square x. That's where I'm getting this from. I can put a little note here that the derivative of cotangent, it's negative cosecant square x dx, right? Obviously everything here is theta instead of x, but that's where I'm getting that from. So I found that in section 3.5, page 150. So then, okay, now that I know this is u, I know the derivative of u is actually here. The only thing is, again, as always, like, you know, there's always this type of problem where we are missing something. What's that something that we're missing? I don't see a negative anywhere here. So I need to just simply add that negative at the very front of my integral. So pi over 4 to pi over 2. Those are the original limits, which, by the way, at some point they're going to change. So all I'm doing is adding right now that negative at the front. Now I don't need to add anything here inside, because adding a negative sign, I mean, it's okay. So then now I can say, okay, I can replace this whole thing. I could have written this negative just to make it clearer for you. Like, you know, these two things are multiplying times one another, right? I could have put the little negative right here at the front first, and in the next step I take it to the outside so that you can see like why. But I mean, it's really the same thing, either leaving it here or leaving it at the front. It's gonna be more useful if you leave it at the front than if you leave it here, but I mean, it's okay. So then I write it here first, but in the next step this little negative goes to the front. And why I put it here, because I really want to replace this by the u, right? And the only way for me to make sense of doing that, or why am I going to do that, is going to be by me understanding that I can put it here, but then I can take it to the front. And it's not that here, I know it looks weird, it looks as a minus, but it's times. These two original functions were multiplying times one another, and that's what they're supposed to be doing when you put or you include this negative here. So now you're going to say, okay, this is going to be u, this is going to be, well, you're going to replace this entire thing by du. So u times du. And this negative, it's not that I just got rid of it or it wasn't there. I send it to the front, and I should keep it at the front. Okay. So now the other thing that I'm pending to do is transform these limits. How? Remember, you're supposed to substitute these values when x, actually theta here, we don't have x's, but when theta is, let's start by the upper limit, it's pi over 2, or the lower limit. Let's do the lower limit first. When theta is pi over 4, what's going to be u? U is going to be, and you know u is cotangent theta. It's going to be cotangent of pi over 4. We solve this, calculator, by hand, unit circle. The answer is 1. When theta is equals to pi over 2, u is equals to cotangent of pi over 2. This is going to be 0. So this is my going to be my lower limit. This is my upper limit. I'm going to be lazy and not write limits, but there it is. So now that last integral, rewrite it. Don't forget you had a negative at the front. If you do, then we're going to do everything wrong. So upper limit is going to be 0, lower limit is going to be 1. We have u times du. So now all we have to do is do the integral of this. If I'm going to do the integral, I do not need anymore that integral symbol. Just say u raised to the 1 plus 1 over 1 plus 1, evaluated from 1 to 0. So all we do is I keep this negative, and whatever I do out of all this at the end, I'll just multiply times a negative sign at the end, my answer. So then this is going to be negative, and this is going to be first evaluate the upper limit. So 0 squared over 2 minus the lower limit, 1 squared over 2. Okay. Then this would be minus, this is going to be 0. So all you have to do is work on this. 1 squared is 1, 1 over 2 is 1/2. There's a negative at the front, but this negative and the negative on the outside, when you multiply them, they make a positive. So basically the answer out of all this is going to be just positive 1/2. Okay, and that's the answer for this problem. For all this. Okay, 1/2. So now, following the same steps, we will solve this one right here to the side. Okay, if it doesn't fit, I'll give myself more room to the right side, but hopefully it does. So first, who's gonna be u? Who's gonna be the derivative of u? Let me probably, I'm extending myself too much and then it's not gonna fit. This, let me put higher, this. So let u be, let me see here. See, I need the multiplication of two functions, a composite times the derivative of the inside of this composite. But this one doesn't have two functions, so then I need to do something prior to using the substitution rule. Let's rewrite this just as it is. We're going to put negative pi over 4 to pi over 4, and then tangent of x, let's use an identity, a basic identity, the quotient one. It says that this can be replaced in terms of sines and cosines by sine of x over cosine of x, right? Okay, so this is sine of x over cosine of x dx. This is an identity. If you remember your identities, your basic identities. So I haven't even done anything. I haven't transformed this in terms of u's and du's. Haven't even changed the limits, transformed the limits, but I just rewrote it so that I could do it because I didn't have the multiplication of a function, a composite, times its derivative, or at least a function, even though it's not a composite, times its derivative. So then now I'm going to do the substitution method. Who's going to be u? U, we can let it be cosine of x, because after all, what's the derivative of cosine of x? It's going to be negative sine of x dx. Okay. Now I know we don't have a negative here, but we're just going to compensate for it and add it in there at some point. Before you do that, let's do the limits already. Let's transform the limits. When x is equals to negative pi over 4, that's the lower limit, u is going to be cosine of negative pi over 4. That's going to be my angle. When you evaluate this, you will get square root of 2 over 2. When you do x equals pi over 4, you're going to get u is equals to cosine of pi over 4. And this is going to be positive, also square root of 2 over 2. So the limit is the same. Yes, kind of weird, I know. But that's what it is. That's what it came out to be. So now you're ready to transform this, well actually this second one, right, into your new integral with your new upper and lower limits, which by the way they're the same both. That's too big. I should leave more space. So this is going to be the integral from square root of 2 over 2, square root of 2 over 2. So what's going to be the transformation? Well, remember that I needed a negative, right, in front of the sign of x. So this negative that I don't have here, let's put it at the front already. Anyway, putting it at the front of the fraction, right in front of the negative sign of x, or in front of the integral is the same thing. So now, sign of x on top is going to be du. In reality, it was supposed to be negative du, but I decided to send the negative to the front. So just du over u, right? So then this, why don't we rewrite it in the following way so that you can recognize it as its proper antiderivative. This is going to be 1 over u times du. All I did is I know there's a 1 here, so I put this as a fraction and I left the du, I send it to the front. Wait. So then my next step is going to be, okay, so now I'm going to think how to integrate this, because I'm ready to integrate it. So that's where you go to section 4.8, and the integral of 1 over u times the derivative of itself of the derivative, that's what du represents, the derivative of u, of the denominator. Then it's, that's the way that you do the derivative of ln of u. If you go backwards, right? ln of u, its derivative is 1 over u times the derivative of the denominator, which is u. So then the formula for integrating this is going to be negative natural log of the absolute value of u. Go to section 4.8 again. Every time I've been going there, I've been showing you where the formulas are at constantly through two videos. And if you go here, you're going to find 4.8. You're going to go to the third page. What I'm talking to you about is number 9, formula 9, 1 over x, but I have 1 over u. So then what's the antiderivative or the integration going backwards? So it's going to be ln of this denominator plus the c. So in mine it's ln of u plus c, but there was a negative, so I must keep bringing down this negative. I should not forget about that. Well, not plus c, because I do have limits. Sorry, I was forgetting that I have limits. I was copying the formula from section 4.8. So what are my limits? Evaluated from square root of 2 over 2 to square root of 2 over 2. Oops. Sorry. To put a bracket here. So here I have this negative that I will multiply times the evaluation of the upper limit is supposed to be this one on the top first, but they're the same, so you don't notice the difference. You think you're just putting the same number because they're the same number, right? So what natural log, every time that I click down it goes lower and lower because of this. Natural log of square root of 2 minus natural log of square root of 2, it's 0. It's like if you're doing the same thing minus the same thing, they cancel each other. So the answer is 0. So what's negative? There's no such thing as negative 0. 0 is a neutral number, and that would be our answer right here. This, notice how, now I know, some of you asked me today in class, what do you mean that you're finding the curve, the area under a curve or something, and that's the answer? Well, this is just not within a context yet. This is just doing the integral of a function, which technically, yes, it's finding you're finding the area between the function and the x-axis, but here, in between those values on the upper and lower limits. Fortunately here, the answer was 0. So, that is it. That's the answer for that one. Not that there's no area, but probably two areas, one positive and one negative, cancel each other or something like that. And that's what happened here. That's what you see happening. Next problem. Let f, this is another theorem, number 8. Definite integrals of symmetric functions. So for the previous integrals, they were definite integrals. We did have an upper and lower limit. We were using theorem 7. Now we're going to use a different theorem because these problems are a little bit different from the other ones. The difference here is that you will have to do the integrals of certain functions that are given to you on purpose as being functions that are either having even symmetry or odd symmetry. This is a concept from college algebra. I don't know if you recall this, but for example, when a function is having even symmetry, it's because if you do f of negative x, the answer is f of x. If you do, and that's even. So I'm going to put a little star here saying that basically what I'm saying here is that if you substitute a negative x into every x of a function, and in the answer, no signs change in every term, that's when you're going to have an even symmetry on the graph, or you have an even function. Even function is the way that I should say it. The function has symmetricity with respect to the y-axis, but this is an even function. An even function is the one that has symmetricity with the y-axis. So no signs change, then symmetry with respect to the y-axis. These are definitions that you need to memorize. I don't think this is going to be, I'm not too sure, but I don't think it's going to be in a formula sheet, because this is something from college algebra that we should know by this point. So an even function is a function where when you plug in a negative x into every x, the result is that the signs do not change from term to term, and then the graph is symmetric with respect to the y-axis. It looks as a mirror image across the y-axis. If you have your function to be an odd function, then when you substitute a negative x into the x, the answer is going to be negative f of x. This means that every sign, this negative times f of x means that every sign in this function will be changed to its opposite. Every single one. So here all signs, wait, that looks like an H. Signs change from every term, all of them, they must change. So if that is the case, then the graph has symmetry with respect to the origin. Okay. So again, concepts from college algebra, you must memorize this because I don't think this will be on a formula sheet. So anyway, so what if I classify one function that is given to me from the integral as an even or as an odd function? Well, that is going to be dictating the way you're going to solve that integral. If your function in letter A is even, then, and assuming that the given interval is the same value, you see the same number but opposite sign. So they're opposite from each other. That's the way this kind of problems are going to be. So you have the function, you decide that it's an even function. This is how you're going to do it. You're going to do the integral of this function, and basically whatever you get, and you're going to do it from 0 to a, and you're going to do it times 2. Why? Because we're probably saying, just to give you a visual example, let's say that we have a function something like this. So then you're going to say, okay, I want to know the area between these two curves, right? So then I want to know the area here. I want to know the area here. This that I'm putting in or coloring in orange. These two sections, let's say that they're symmetrical across the y-axis. They're a mirror image across the y-axis. So whatever the area is on the left piece is going to be the same on the right piece. So then, isn't it the same as calculating the area of a single piece and then times 2? That's the reason for this. Now, the limits are going to have to be, even though they were given to you as negative a to a, you're going to change them to 0 to a on purpose, because you're going to calculate from 0 right here at the origin all the way to a being this number right here. This is going to be 0, and this is going to be a. And then whatever you get out of this piece right here, then you just do this times 2, and that's going to calculate the total area for these two pieces. Now, if your function is odd functions have the characteristic that they are a reflection sort of in a diagonal way. So to give you an example, let's say that you have this kind of graph. Let me think of something that could be. So you have something like this and something like this. Yeah, something like this. And let's say you want to calculate from negative a to a, like what's the area? Let's say here you're cutting it like this. Oh, and by the way, I didn't say here, this is your negative a over here. So I want to know what's the area here and what's the area here. So this type of functions have a reflection in a diagonal way. Imagine that you have an invisible line that goes through here in diagonal. Are in these two pieces a reflection of each other? Yes, they are. So if that's the case, that's the example of a not function, then you're going to do the integral just the way that it's given to you, but the answer is always going to be 0. Every time you calculate the area of a function by pieces, and one piece is symmetrical to the other one across the origin, and therefore one piece is going to have to be below the x-axis, the other piece is going to be on top of the x-axis. It could be vice versa, first one on top, second one below. When you add this negative part plus this positive part, negative because it's below the x-axis, positive because it's above the x-axis, they're going to cancel each other, and the answer will always be 0. That's sort of a shortcut, an easy one, a nice one. So okay, let's see what this is going to be in example number 3. So first of all, let's determine, is it even or is it a not function? How? I'm going to do this. I'm going to substitute in every x of this function a negative x on purpose. To determine whether it's going to be an even or a not, it doesn't matter, you're going to do the same process all the time. So what's the negative x to the 4th power? Well, technically you have to do negative x times negative x times another negative x times another negative x. That's going to be a positive x to the 4th. Every time you have a negative x raised to an even number, the answer stays positive. Or do the entire multiplication if you want 4 times until you realize this is going to be positive 4x to the positive x to the 4th. Sorry. Then you have a minus 4 times, what's going to be negative x times another negative x here? It's a positive x squared. So here, I'm just going to rewrite this a little bit, x to the 4th minus 4x squared plus 6. This is my substitution of the negative x into every x. What was the result? The sign of the first term here is positive, the sign here is still the same. It did not change. The sign of the second term is negative, the sign here did not change, it's the same. The third term is positive, this did not change. All of them are the same. So no signs change. What does that tell me? No signs changing? That means it's an even function, because if all the signs would have switched to the opposite from one term, comparing term by term or term per term, then you say that that's an odd function. But mine is an even function for this one. So then I'm going to go with letter A. I'm going to solve this integral by transforming the limit on purpose from 0 to positive 2. The negative 2, basically, you're just going to replace it by a 0 and do the integral of this. These are not that difficult. So then, okay, after all this, I'm going to rewrite this as the integral from 0 to 2 to positive 2 of x to the 4th minus 4x squared plus 6 dx. So then what I'll do is I'm going to do the evaluation of the integral already. So x to the 4th is going to be x to the 4 plus 1 over 4 minus 4 times x to the 2 plus 1 over 3. The integral of 6 is going to be 6x. You don't need the dx anymore. You actually need to indicate what is your lower and upper limit. So x to the 5th, I forgot to put here plus 1, sorry, over 5. Here, I put the answer instead of taking you step by step. I'm so sorry that I'm keeping some steps around. So 2 plus 1, but you know it was going to be 3. Minus 4x to the 3rd over 3. Okay. What if you rewrite this? I mean, you can leave it like this, or you can write the fraction 4/3 and leave the x to the 3rd to the side. It's the same thing. Thing is, you're going to evaluate it here. Okay. And whatever the answer I get out of this, remember, I'm going to do times 2 because that's what the theorem was saying. You may do times 2 at the end, or you may keep the 2 at the front. That 2 that I just told you, you may keep it at the front, you may keep it at the front, you may keep it at the front. I should not have removed this. So then 2 times, I'm going to evaluate this. First with the upper limit. 2 to the 5th power over 5 minus 4 times 2 to the 3rd power over 3 plus 6 times 2 minus, put a parenthesis, 0 to the 5th over 5, oops, this is a 5, minus 4 times 0 to the 3rd over 3 plus 6 times 0, and that's the entire thing. Okay. So the 2 stays as it is. You can see pretty much this is going to be a 0, this is going to be a 0, and this is going to be a 0. So we're just going to have to simplify this first expression. This is going to be a 32 over 5. 2 times 2 is 4, 4 times 2 is 8, 8 times 4 is 32 thirds, 6 times 2 is 8, not 18, sorry, 12. And so now you may use the calculator. You may put here, let me remove this thing, in parentheses 32 over 5. If you do not use the parentheses, more than likely I think you would get the incorrect answer because of the fraction. So as a fraction, that is 1/16 over 15. So now just do that answer times 2, or if you put it together, like make sure you do this, times 2, that would give you the same exact thing. Change it as a fraction, 232 over 15. 232 over 15. That's my final answer. That is the area between, using this function from -2 to 2, but we had to change the limit from 0 to +2 because of the theorem, and multiply times 2 my answer because of the theorem saying that if the function gets classified as an even, I have to do this. So first I need to determine if it is an even or if it is not, and the only way to determine that is always substituting a negative x. If no sign change from term per term comparing, then for sure it's going to be an even. But if all the signs change to the opposite of what they used to be, and it has to be every single term, then you classify it as a not function, and you would say the answer is always going to be 0. You can work it out just to prove that it's going to be 0, but I can guarantee it's going to be 0. Okay, so that's that problem. Next one, area between curves. So far we've done, in the previous section, area between a curve and the x-axis. That was in the beginning of the previous section. That I did in class. I didn't include that explanation of that kind of problems in the video anymore of section 5.5, the previous one, because those I got to do them in class. I did have time for that. So now you're going to be given two functions, and you have to find the area between them. How? Graphically, and a simple explanation is that you want to form rectangles. Vertical rectangles, by the way. And it's important that I say vertical and I emphasize that, because then we're going to find a way to find the area between two curves with horizontal rectangles. So here you have the upper curve, let's say, and the lower curve. Okay, so usually f of x is going to be used to denote the curve that is going to be on the top, and g of x is going to be used to denote the function that is going to be at the bottom, enclosing this section, right? So that's just to give you a visual idea. Okay, what's the formula we're going to use? It says if f and g are continuous, with f of x being greater than or equal to g of x. So this one on top, obviously it's greater than this one. That's kind of obvious, right? Why it's greater? Because it's on top of the other one. Throughout the interval from a to b. So you're going to have the interval from a to b. Those are going to be its values. Those are going to be your lower and upper limits. F of x then minus g of x is going to be the way to do to set up your integral and then evaluate that integral. So the area of the region between the curves is going to be y being f of x, and also you have your g of x function from a to b, and so it's the integral of the subtraction of these two from a to b. Okay, so the x that is mostly to the left is going to be your lower limit. The x that is mostly to the right side is going to be your upper limit. So you can probably see that clearer here. That's your a, that's your b. That's like your boundaries, the limiting a space from left to right side. What's the limiting your space from above and below, let's say? Well, the actual function. F of x is always going to be used to refer to the top function, the higher than the other one, the greater than the other one. And g of x has to be the smaller one. So here we're going to solve this problem that says, let me enlarge this. This one says, so we have to find the area of the region bounded by the curve y equals 2 times e raised to the negative x plus x. Below, it's bounded above by this curve. Should probably highlight that. Find the area of the region that is bounded above by this curve. It's bounded below by this curve. So on top, it's that one. On the bottom or below, it's this one. On the left, by x equals 0, and on the right, by x equals 1. So it's basically what I explained to you this. X equals 0, x equals 1, and there's going to be two functions. It's even very self-explanatory, telling you which one is the largest one, which one is the smallest one, which one goes on top, which one goes at the bottom. So find the area of the region bounded by the curve, okay? So I need to set up an integral. This integral is going to represent the area from 0 to 1. So which one is the one that is above? This one. So this one right here is my f of x. The one that is below, what's above? This is my g of x. What does the theorem say? F of x minus g of x. So then 2e raised to the negative x plus x minus this e raised to the x over 2. Should probably write it as vertical. That'll make more sense to you. E to the x over 2. So what do I do next? This is with respect to x's, because that's all the type of variable that I have. And now let's start to evaluate this. Okay? So piece by piece, I'm going to be evaluating this by saying, okay, we can do the chain rule, but backwards, right, for this. Like what would be the antiderivative of e to the negative x? Probably this right here, number 8. E raised to the kx. So what do I have as kx? It's my negative 1x. What's the antiderivative of that? 1 over k. Let me make it bigger. 1 over k. What's the k? The number in front of the x. What's my number in front of this x in the exponent? A negative 1. So 1 over negative 1 times e raised to the same thing as in here, to the negative x in my case. So then this is going to be, there's a 2 by the way, and that 2 you just have to keep it in there. 2 times the antiderivative of this, or the way to integrate that, is 1 over negative 1 times e to the negative x. I'm just following the formula that I just presented to you right here in section 4.8, page 265. So I'm going to simplify that in the next step. The antiderivative of x is going to be x to the second over 2. Trying to rush through this and I skip steps. Should not, I should show you every step. So that's it. Minus this, how can we rewrite this? So you could say that I can rewrite this as, what if I put a 1 here, and this thing I send it to the front, and I just keep it there. Just like I kept the 2 multiplying times this, I'm going to keep the 1/2. And let's do the antiderivative of e to the x, which is going to be itself, e to the x. Because if you recall before, like when you have y equals e to the x, what's the derivative of e to the x? Itself. When you're going in this direction, where you're going backwards, I mean, it's the same thing, but basically, it's based on this. This is what you have, e to the x, this is the antiderivative. But the derivative of e to the x by itself is 1 over 1, because that's the number in front of the x. 1 over 1, e raised to the 1x. So basically, 1 over 1 is 1 times e to the x, e to the x, right? So then, I'll simplify that right now, and I'm going to evaluate this from 0 to 1. So I just did the derivative of each of these terms, this one, this one, this one, piece by piece. So then 1 over negative 1 is negative 1 times 2 is a negative 2. Negative 2 e to the negative x plus x squared over 2 minus 1/2, put it too high, click here, minus 1/2 e to the x. There's nothing to simplify in there, it was just this part and this part, from 0 to 1. So what do I do? Evaluate. First the upper limit, then the lower limit. So it's going to be first negative 2 times e to the negative 1 plus 1 squared over 2 minus 1/2 times e to the first power. Minus. Same thing, but now with a 0. E to the negative 1, it's, I mean, you can write it as a decimal, but I don't think the need for that. We have the need for that. All you're going to do is rewrite this as a fraction where the 2 stays on the top, the e goes back, and because it goes back to the bottom, this is going to change to a positive 1. You don't need to even show the 1. Just leave it like that. Leave the negative, leave the 2 where it is, send this to the denominator of the fraction, and the exponent turns positive. 1 squared is 1 over 2, it's 1/2. Minus 1/2 e, because e to the first power is the same thing, is itself. Minus, let's see what we can simplify here. E to the 0 power, that's a 1. So negative 2 times the number 1. What's 0 squared? 0 divided by 2, 0. That was a minus. Minus 1/2 times a 1 again. So then, let's distribute the negative in the second parenthesis. Positive 2, 2 times 1 is 2, right? Well, negative 2 times 1 is negative 2 times a negative, positive. The 0, well, doesn't count, we kill it. Negative 1/2 times 1 is negative 1/2. That negative 1/2 times a negative, positive 1/2. So now all you do is simplify this. So, the things that we could combine is probably this one, and this one. Only the numbers that don't have any sort of variable. 1/2 plus 1/2, that makes a whole, plus 2 is 3. The 3 you can leave it until the end, or you can write it already, it's up to you. There's nothing you're going to do with this. Okay, so this one is this one. The only one that you could try to rewrite a little bit so that it looks a little bit better is minus e, send it to the top, 1 times e is e over 2. And then at the end, you're plus 3. So the plus 3 is because of these three together. Okay. And well, this one, what's this? And that's it. That's as far as you can go. That would be our answer. So approximately this, if you're like, what's this in decimal, what's the area? Put it into your calculators, and this is what you get. I had already done it. So you put parentheses, -2 divided by e, parentheses minus e over 2 plus 3. Oh, you need a parenthesis there. Why 2 4 decimal places? I mean, just because. That's how the book had it. In a multiple choice question, then just check how far you need to go. Do you even need to write the answer in decimal form, or maybe not? So that's this one. Example number 5. Okay. Now we need to find the area of the region enclosed by the parabola y equals 2 minus x squared and the line y equals -x squared. So they're not being very explicit on this problem and telling us, okay, this function is the one that is going to go above, this one's going to be below, what's going to be my left limit and my right limit, let's say, or my lower limit and my upper limit. The x limits are not given. And I don't even know which formula goes above, which one is below, so to know which one gets subtracted from which, because remember that it's supposed to be f of x minus g of x all the time. So I don't know who's f of x, who's g of x at this point. They're not telling me which one is above and which one is below to determine that. So you have to do the graph for this one. So y equals 2 minus x squared. We may do a little table of values if you want for each of these and just do the graph. So then we're going to say, what if I at random put a 0 here into the x? The answer is going to be 2. If I put a 1, that's going to be 1 squared. 2 minus 1, it's going to be a 1. If I put a 2, maybe 3 points is going to be enough. If I put a 2, it's going to be 2 squared is 4, so 2 minus 4 is -2. Let's see how this is going to look. So this is going to be a point at 0, 2. And I'm going to need a 1, I'm going to need a 2, I'm going to need a -2. So there's going to point at 0, 2, there's going to be a point at 1, 1, there's going to be a point at 2, -2. Kind of there. So then, this says that this should look as a parabola. So, was this right? 1 squared, it's a 1. I was like, why does it look weird? This one right here. My algebra was right, but I plotted the point in the wrong place. So 1, 1 is supposed to be right here. This parabola is going to run something like this. Something like this. This is one piece, right? Now, can I have something on the negative side? Yeah, I can just add an, if you want to see something on the negative side, let's say -1. What would be -1 squared? It's a positive 1. 2 minus 1, it's a 1. So now we have another point at -1, 1. Can we have more points? Yes, I mean, why not? But I mean, I just wanted you to see that this really, I could continue plotting points on and on and on. But that's just, I just want to get a general shape of this, to know which one is going to be above and which one is going to be below. Like, I want a visual of this. So here, let's plot again any numbers that you want. So let's say that I'm going to go with some negatives and some positives. Let's say that I'm going to put -2, -1, 0, 1, and 2. So why for this one I did one more than this? I don't know why, just because. What happens if I put a -2 into this x? -2 times a negative, 2. What happens if I put here -1 times a negative, +1? 0 is neutral, this is -1, this is -2, right? So then we plot points for this one now. So we're going to say, okay, this is going to be at -2, so now I need this space for -2, 2. What kind of graph you're going to make here? A line. Then you're going to say -1, 1, so you see how this point coincides with the other one. This was already a point on the other graph, and this is coinciding. Why? You'll see why right now, and that's an important fact that we will use right now. 0, 0, 1, -1, and then 2, -2, and this point is coinciding as well. So then I draw my line. Try to do as best as possible this line. I'm gonna do it with the tool because it doesn't seem like it's gonna help. Okay, just that. So the line, let's say that it goes from here to here. Way better, right? So then was passing through this point, through this point, through this point, through this point, and to this point. So okay, what about this? I think we can all see already who's going to be the upper, not the upper bound, but the, how's it named? The graph that is going to be greater than the other one. The one on top of the other one is the curve, the parabola. This is going to be f of x. The one that is below the other one, it's going to be g of x. That's the smaller, greater, and smaller. F of x is greater than this one, g of x is smaller than the other one, however you want to see it. Now, I need to find, I already found something graphically just by looking at this. But I need to find the points of intersection, which I already found them technically. What if ever you have trouble graphing and you don't find the points like me, that I was a coincidence that I found the points of intersection? Well, you can find the points of intersection algebraically, and that's important. You'll understand what those are going to be right now. Of the two graphs, right, obviously. You're going to equal the equations to each other. Doesn't matter which one goes first. Just put them equal to each other and solve for x. So how do you solve for x? I was going to move this one here, but you know what? I do want to have all the terms on a single side, but I'm foreseeing something ahead of time. When I put all the terms on a single side, whether on the left side of the equal sign or on the right side of the equal sign, I will end up with a trinomial. So let's move over these two terms to the right side. And why not the negative x to the left as I was going to do first? Because I want the term that has the biggest exponent on purpose not to be negative. That would complicate things a little bit more for us. So the term that has the biggest exponent, because I can foresee ahead of time what's coming already, I'm going to make it to be positive by sending everything to the right side. Write it from greatest exponent to smallest exponent in that order, this expression or this equation. So you have 0 on the left because nothing's left. The only way to solve for x here to find the points of intersection is going to be factorization, and that's what I was seeing ahead of time. That's why I wanted the x squared to be positive. So 2 times 1 is 2, and if you subtract them, it's the one in the middle, a minus and a plus. This is, again, basic factorization. What kind of factorization? A trinomial. If you have trouble, then look for how to factor trinomials. And so what's the point of intersection? Or in the points of intersection, I should say, plural, more than one. It's going to be this 2. You solve for x, this is 2. You solve for x here, this is -1. Look exactly at which 2 points these two graphs were coinciding. They were having the same points in common. A 2 and a -1. A 2 and a -1. That's not -1. When x was 2, the answer for both is the same on the y. When x is -1, the answer for both is the same. So that means These are not points at random. These are special points. Let me put them with this one. This point right here is the point -1, 1. And this point right here is the point 2, -2. Those are the points of intersection. Those are going to be my lower limit and my upper limit. Okay. So I am interested in finding the area inside, formed by the inside of these two graphs, these two functions, but only strictly between x equals -1 and x equals +2. Only between x equals -1 and x equals +2. So on the left is bounded by -1, on the right is bounded by 2, at the bottom is bounded by the equation y equals -x, that's g of x, and at the top is bounded by the equation that is the parabola, 2 minus x squared, which is this one. 2 minus x squared, and this is -x. That's how it's bounded. Even though they were not telling me, this is the kind of problem that you want to be able to do, where you graph and you determine all these boundaries, left, right, bottom, top. Now you're ready to set up the integral. So I think I'm going to use this space right here. The area is going to be the integral. What are going to be my lower and upper limits? My x's, from -1 to 2. Obviously, the bottom one, the lower one, is the more negative one, or the one on the left side. The upper one is the biggest one, the one more to the right side. So then, I'm supposed to do f of x minus g of x. So 2 minus x squared minus g of x. Always the one on top minus the one at the bottom. That's what this theorem was saying. F of x minus g of x. Next, we will say a is equals to, let's simplify this. Oh, and I forgot to put with respect to it. 2 minus x squared plus x dx. Is there anything to combine? I don't think so. There's nothing to combine. You may leave it in this order. You may put it in order from greatest exponent to smallest. Really doesn't make any difference. Start evaluating. So what's the antiderivative of 2? 2x. What's the antiderivative of x to the second? You're going to add 1 to the exponent. That's 3. You're going to divide by the exponent plus 1, which is 3, so over 3. Plus the same thing here. Add 1 to the exponent that this x has, so that's x squared. Divide by that, 2. Sorry, you don't need the dx. So you're evaluating this from, I don't know why I put it here, from -1 to 2. But I'm not doing the integral anymore. I'm evaluating the integral already. So then it's going to be 2 times the upper limit minus 2 to the third power over 3 plus 2, which is the upper limit, over 2. All this minus 2 times -1 minus 2 minus -1 in parentheses to the third power over 3 plus 1 to the second power over 2. Looks like a z, but it's a 2. So you simplify all this. 4 minus, this is going to be 8 thirds plus 4 over 2, which is what's 4 over 2 is 2. -2, -1 to the third, it's a -1 over 3 times a negative, +1 over 3 plus 1 over 2, right? Because 1 squared is going to be that. Distribute the negative. Before you distribute the negative, why don't we simplify? 4 plus 2 is 6 minus 8 thirds. positive, I'm gonna, yeah, let's get rid of this. We don't need that anymore. Positive 2, negative 1/3, negative 1/2. So A is equals to, combining the terms, I mean, not combine, you can really combine everything at once if you want to. We could do that. Just be careful how you put it on the calculator. 6 minus 8/3, parenthesis, plus 2, minus 1/3, minus 1/2. Notice how every fraction I set it up in parentheses. 4.5, which is the fraction is 9/2. You could do this step by step, but I mean, I was going to, and I said, nah, let's just do all the simple additions with the calculator. So I have, okay, the next one. Okay, so that's the process for this one. This is the same process. You have to do the picture so that you understand what you're dealing with and what are going to be your boundaries and all that. Find the area of the region in the first quadrant. So they're already telling you in the first quadrant that it's bounded above by the square root of x, y square root of x. You're going to do a t-table for that. Probably a short t-table. Then, and below by the x-axis. Okay, so below is the x-axis and the line x minus 2. Okay, so the x-axis is just there, right? We know what that one is. But for this one, we also want to do this. Notice something interesting, the way that this is written or worded. It says, find the area of the region. The region is for sure in the first quadrant. It's bounded by what? What are the boundaries? Above, by the square root of x. Below, by the x-axis. And also below, by this other equation. How could it be that there's two boundaries below? We'll see right now. So here, square root of x. Do not put negative numbers, obviously, because that's going to be undefined. So you can put a 4, a 0, a 4. You could even put a 1. I don't know why I didn't think of 1 before. 1, 4. You may put other numbers if you want, but maybe that's enough. Square root of 0, 0. Square root of 1, 1. Square root of 4, 2. Here, what numbers should we put? Whatever numbers you want. Let's say we put 0. Let's say, because anyway, everything is going to be happening in the first quadrant, so I don't need any negative x's. Why bothering now? So 1, 2, 1, 0, 1. Put a 2. This one, because I already know what's coming up, I'm going to do more. So 0 minus 2, negative 2. 1 minus 2, negative 1. 2 minus 2, 0. 3 minus 2, 1. 4 minus 2, 2. Okay, so we plot the point. So I'm going to need 1, 2, 3, and 4. I'm also going to need 1, 2, 3, and 4. The bottom just up to negative 2. I don't need anything here. So I'm going to plot a point for 0, 0, 1, 1, 4, 2. Okay, that's that graph. Okay, so then what's the next thing to do? Let's graph the other one. 0, negative 2. I mean, I'm going to plot the point, but remember, all the action is going to be happening in quadrant 1. So I don't even need to do any point or plot any point on the negative side of the y-axis or x-axis, but yeah, I'm going to put it. 1, negative 1, 2, 0, 3, 1, 3, 1, okay, yes, here. 3, 1, and 4, 2. I already find a point that coincides with the point on the other graph. Okay, so now we draw the line. Let me do it better. But okay. So then I'm going to find the area. Sorry, where did my toolbar go? Of this inside piece. Now, be very careful with what you're gonna say, because what were the boundaries? The x-axis was one of the lower boundaries, or below, and also this line. And all the area you want to find is whatever falls in quadrant 1. So when we do this, what we're saying is that we're trying to find only this, the area enclosed by these 4 things, by this curve, by this line, and the x-axis. The x-axis right here, this is also one of the boundaries. That's why it's only this sort of, let's say, triangle there. No, it's not a triangle because it's circular here, but sort of looks like that. Okay, so what do we do now? Let's find the points of intersection again. Okay, so even though I already know one point of intersection, I know this could be probably another point of intersection right here where this green line and the orange one meet. Also probably here in the origin. But anyway, let's do it. So how do you do it? You set equal to each other the 2 functions. Doesn't matter which one is first, doesn't matter. So the only way to solve this would be solve for x by first getting rid of the complicated square root of x. So for you to do that, you raise to the 2nd power on purpose both sides. So on the left side, you're going to end up with x. On the right side, you're going to have to FOIL x minus 2 times x minus 2. So FOILing this is x squared, negative 2x, positive 4 equals x. Simplify this. Then we send this poor little x over here together. And this we can write it here because that's going to be the one that I'm going to combine it with. Plus 4 equals 0. Now factor again, just like the previous problem. So go over your factoring rules. X times x, 4 times 1, minus and minus again. So this is going to be a 4 and a 1. Okay, now, is 4 a point of intersection? Let's check or verify with the graph. At x equals 1, 2, 3, 4, is there a point of intersection? Yes, totally. 4, 1. At x equals 1, and how can I check that? Look, 4, not 4, 1, sorry, 4, 2. 4, yes, it was located at 2. 4, 2. These 2 points are the same. It's a common point for both. Is x equals 1 really a point of intersection in reality? Look at this one and look at this one. I don't think it's a point of intersection. You have a 1, you have a negative 1 here. So it's not really a point of intersection. This is called an extraneous solution. That means that it's not really, it's an extra solution, but it's not really the solution. This is the only solution. This is the only point of intersection given by solving algebraically. I know there may be more points of intersection between the graphs because I can see here these 2 graphs are meeting here, they're meeting here, they're meeting here. I mean, I know there's more. But as far as those 2, we're going to kind of discard this one. We're just going to ignore it. So we're gonna say that the interesting part comes. Bounded by y equals the square root of x above, and below there's two things that are bounding this area below. The x-axis at some point, and the orange line y equals x minus 2 at another point. So this is how we're going to handle this. One interval is going to be from the number 0 up to the number 2. That's going to be one single interval. The other interval is going to be from the number 2 all the way to the number 4. Why? Because, what color do I use? So you can make sense of that. Imagine that something that I have not used. This one. This is going to be one boundary on the left side. This is the boundary on the right side of this first interval. This is going to be the left boundary of the second interval, and this is going to be the right boundary on the right side interval. So there's two. Okay, from 0 to 2, from 2 to 4. This is one, this is another one. Because if you see, and I'm going to color in different colors this now. So let me color it differently. Yeah, look at this color, that it looks slightly different than this green. This interval is bounded below by the x-axis, on top by the square root of x, on the left side by 0, on the right side by 2. This other piece, this green piece, it's bounded below, not by the x-axis, because it's not sitting on the x-axis anymore. It's sitting on the line y equals x minus 2. That's below this other graph. So the above is the square root of x, the below is x minus 2, the left side is 2, the right boundary, or the lower limit is 2, the upper limit is 4. So you're going to have to calculate this doing two separate integrals and then adding their answers, and that would be your total area. Okay. So we're going to say, okay, there's going to be two regions that I'm going to find the area, and then I'm going to add them. So for the first region, it's going to go from 0 all the way to 2. So how are you going to do the integral for this? You're going to say the area for this region is going to be the area bounded from 0 to 2, from left to right. That's going to be from here to here. The one on top is the square root of x minus the x-axis. What's a way to write the equation for the x-axis? The way to write an equation for the x-axis for this green line, it's a line that is passing through the origin, through the number 0 in a horizontal way. So it's a horizontal line at y equals 0. But this can also be written, since I'm going to use the theorem, as g of x equals 0, right? Because the theorem says you're supposed to do f of x. What's going to be f of x? This one. Minus g of x. So what's going to be f of x? The one below. So on top was the square root of x minus the one below, minus 2 minus x. No, x minus 2. So here I don't think we can simplify other than distributing the negative. Minus x plus 2 dx. I forgot to put dx. Let's start doing the integration of this. So then we're going to say x to the 1/2 plus 1 over 1/2 plus 1 minus the integration of this is x to the 1 plus 1 over 1 plus 1 plus 2x, all this integrated from 0 to 2. So then this is going to be x to the 3/2 over 3/2 minus x squared over 2 plus 2x from 0 to 2. So why don't we do as we've done several times? 1 over 1, so this is going to be 2 over 3 x to the 3 halves minus x squared over 2 plus 2x from 0 to 2. And now you evaluate this. So first the upper limit, 2/3 times 2 raised to the 2/3 minus 2 raised to the second power over 2 plus 2 times 2. All this minus the lower limit, 2/3 times 0 raised to the 3 halves minus 0 squared over 2 plus 2 times 0. What's going to be the second part? All of this is going to be 0, no matter what you do with it. So just focus on simplifying this. 2/3 times the square root of 2 to the 3rd power minus 4 over 2 plus 4. So then all this is going to be 2/3 basically times the square root of 8 minus 2 plus 2. 2/3 times, let's simplify this into the multiplication of 2 times 4 minus 2 plus 4. Yes, I'll combine some things, I know, I'll do it right now. 2/3, this is going to be times 2, times the square root of 2 times the square root of 4 minus 2 plus 4. 2/3 times the square root of 2, there's nothing you can do, but the square root of 4 is 2 minus 2 plus 4. Now keep in mind that you cannot do 2 minus 2. I know you want to do that, but you cannot combine those two. This is a single term. So first, simplify this into something else by multiplying what's possible to multiply. So the 2 times the 2 is going to be 4/3 square root of 2. So this is a single term. See, so that's why you couldn't combine those two 2's in the middle. Then you just bring down what's a negative 2 plus 4 is going to be a positive 2. So that would be the area for the first part. Okay? So then, that's not the final answer. Why? Because this is just the answer for what? The answer for this tiny piece right here. But I want to know the area bounded by the x-axis and by these two curves. So I still need to do the area for the green piece. Is it necessarily going to be the same size as the other one? Not necessarily. Look at the intervals are different, the size may be different, because it's bounded by a curve, not by something like it's straight on the top. So it may be bigger, it may be smaller, who knows? I mean, until we find out, until we do it, is we're going to know. So this was region 1. Now the region 2 goes from 2 to 4. So from 2 to 4, then what's going to be the formula for the area? It's going to be 2 to 4. What's going to be the top? It's also square root of x minus, I just checked something. I made a terrible mistake. And I say terrible because now I'm going to have to fix the whole thing. Okay. Sorry. Look at this. What was the above boundary of the first piece, sort of in like purplish? It was the square root of x. What was the bottom piece? X. The x-axis. But what was the x-axis going to be? Just simply 0. That was the function y equals 0. G of x is equals to 0. So I didn't have this second one. I mixed two things. The lower boundary was just this, y equals 0. So here I'm going to have to fix the whole thing since the beginning. Here was minus 0. Sorry, I'm so sorry. So then this, there's nothing of this here. It's just the dx. Bear with me, okay? Square root of x minus 0 It's the square root of x. Why? Again, because I made a mistake. I was doing this piece right here where I'm putting a dot. The lower is the x-axis, which I already made an equation for that, and it was the value of that equation is just the number 0. And the top was the square root of x, and it's always f of x minus g of x. G of x for this piece was not the line yet. That was for the second piece that I was barely going to do. Sorry. So then it's just taking off all the extra work, the extra pieces. This, this is correct for this, but we don't need this because we don't have that anymore. From 0 to 2. So it was kind of easier. Less work at least. From 0 to 2. From 0 to 2. From 0 to 2. Okay, all this crazy stuff, forget it. We didn't need all this. And I realized until right now, sorry, I think I'm getting tired. Okay, so this minus 2/3 times 0 raised to the 3/2. Which again, this is going to be 0 anyway. But this first answer was going to be way different. So much simpler. 2/3 times the square root of 2 to the 3rd. So that's going to be 2/3 times 8, which is 2/3 times the square root of 2 times 4, which if you break this apart is 2/3 times the square root of 2 times the square root of 4. Which if we rewrite this, so I still had things from the other thing, when I did the mistake. So this is going to be, the final area is going to be 2/3 times the square root of 2 times 2, because the square root of this 4. So it's going to be 4 square root of 2 over 3. 2 times 2 is 4, you leave the 3 at the bottom, you just rewrite your square root of 2. Let me take off all this. That's the area of just the top piece. So this now I need to put it higher because I should not leave that much space. Okay, that's the area of the first piece, the one on the left. That's the true area for this. Now the area for the second one, let me take a closer look again. The top boundary is this curve, square root of x, and this one. The bottom boundary for this one, because you have to sort of, let's say, ignore this piece. What's the bottom of this? It's not sitting on this x-axis. It's sitting on this line, x minus 2. So that's going to be the lower. That's going to be your f of x. So for this one, this is going to be f of x, but this one is going to be g of x. So just be careful with that and don't do my mistake. So the left or the lower boundary is 2, the right boundary is 4. So for the region from 2 to 4, the area, and I realized because when I was going to start setting this up, I said, why am I subtracting again kind of the same thing? Because I was going to do the square root of x minus, and now you do say the other one, x minus 2. So in reality, I was doing with the wrong limit this thing, this function, right? This subtraction, dx. Keep creating the dx every time. So 2 to 4. Let's rewrite this already as x to the 1/2, simply for the purpose of the moment that I'm going to do the integration, minus x plus 2. So now you do the integration. So it's going to be x to the 1/2 plus 1 over 1/2 plus 1 minus x2 plus x1 plus 1. Over 1 plus 1 plus 2x evaluated from 2 to 4. Let's clean this a little bit. So this is going to be 3/2. This is also going to be 3/2. This is going to be x squared over 2 plus 2x from 2 to 4. 1 over 1 right here. So this is going to be 2/3 x to the 3/2 minus x squared over 2 plus 2x from 2 to 4. So here comes the actual evaluation. So then 2/3 times 4 raised to the 3/2 minus 4 squared over 2 plus 2 times 4. That's just the upper limit. Now we have to do the lower limit. So then this is going to be 2/3 times 2 raised to the 3/2 minus 2 raised to the second over 2 plus 2 times 2 in the bracket at the end. So let's simplify all this. Two-thirds times, we're going to rewrite this as the square root of 4 to the third minus 4 times 4 is 16 over 2. Simplify that in the next step. This is plus 8 minus 2/3 times the square root of 2 to the third power minus 4 over 2 plus 4. So next, 2/3 times 4 times 4 is 16, 16 times 4 is 64, the square root of 64 is basically 8, 16 over 2 is minus 8, plus 8, a bunch of 8, minus 2/3, 2 times 2 is 4, 4 times 2 is 8, so times the square root of 8, minus 2, plus, not plus 2, plus 4, I was thinking of the answer already, of that. So then this is going to be 2 times 8 is 16. 16 divided by 3 is going to be just 16/3. Minus 8 plus 8. Right, because this was this. Let's simplify this a little bit before I distribute. This can be written as this. I'm going to focus on simplifying that part before moving forward with anything else. Well, these two, they can cancel, no? So, can be this. 2/3. What's the square root of 4? 2. Leave inside the 2 doesn't have a square root. Okay? So this one would be this one right here. And this one would be, sorry. That 2 that I circled there is still this 2. I don't know what this is. Okay. And the 2 that I put on the outside is the answer of the square root of this number here. Okay, so negative 2 plus 4, that's going to be a positive 2. So A equals 16/3. 2 times 2 is going to be 4 right here. 4 square root of 2 over 3 minus 4 square root of 2 over 3. And then, so I distributed already this negative. Now let's distribute it here, minus 2. So when I combine this, could I really combine this? Let me see. No, I don't think you can. Even though the first two fractions have the same denominator, it's not going to help you in any way to combine these two into a single fraction, so do not do it. And let me see, what was the answer? 4 square root of 2 over 3. No, you don't want to combine these two. Like, I'm going to write this and then I'm going to take it off. Some of us may think, well, can I at least do this? Like, would that help? Not going to help. Because the next thing is you're going to add this answer from the area of the second piece to the area of the first piece. And it's going to be easier if you keep them like this. Okay, this answer you will add it with this answer. First answer was the area for this first piece on the left, bounded by the x-axis, bounded by this line, bounded by this curve, on the interval from 0 to 2. The second answer that I got is the area for this piece, bounded by the line y equals x minus 2, by square root of x, and by 2 and 4. So now here comes the moment of adding for the total area. So what do you want to write first? Doesn't really matter. Let's write the first answer you got, 4 square root of 2 over 3. This is, this is this. Plus, and just rewrite all this, 16 thirds minus 4 square root of 2 over 3 minus 2. Ooh, so what's the total area? Luckily for us, those two cancel each other. So you end up with 16 thirds minus 2, which you can easily put it on the calculator. 16 over 3 minus 2, math, enter, enter, 10 thirds. That's your answer for the total area. Bounded by all these curves. Okay. That's basically it. This is a nice problem. Nice problem. Okay. Not difficult. Just these are lengthy, but they're simple. Okay. This is an extra slide. I don't know why it's sitting there, just doing nothing, taking space. I just took it off. I guess it's not gonna let me take it off. I'll take it off from the PDF file. Not gonna let me because I'm recording. Yeah, take it off from here. So I'll take it off later. It's not. So now the last problem. We're gonna do one last problem. You know how, I'm gonna go back. We were used to finding the area. All this that you're doing is a short version, and I say short, you're gonna say short. This wasn't short at all, like this one, much less this one. But believe me, this is the short version of you getting the area as we were doing in the previous chapter, where you were drawing rectangles and finding the width of the rectangle times the height of the rectangle, the area of the rectangle plus the area of the next one plus the area of the, it was just a mess. It was a lot of work. And those rectangles, by the most part, were vertical rectangles, right? Well, now we're gonna see that we can find the area using horizontal rectangles. What's the difference? Just a different way of getting the same thing. But having horizontal rectangles is something that is called integration with respect to the y. Before you were doing integration with respect to x, okay? But now it's with respect to y when your rectangles are horizontal. So now you're going to be bounded on the sides by functions that are going to be written in terms of y, not in terms of x. And then your limits, your lower and upper limit, are going to be y values. Okay? Now I'm going to tell you something. Always by default, because I don't think I put it here. No. Always, you're going to say the following. That now look how you're going to do the subtraction of f of y minus g of y instead of f of x minus g of x, because the functions are going to be written in terms of y's and not x's. But besides that, f of x is always going to be your, and not f of x, I should say, f of y, it's always going to be the right function, the one on the right. And g of y is always going to be the left function. Just for you to know, that's never going to change. But we're still doing the formula f minus g. So it has to be the one on the right minus the one on the left. The lower and upper limits are going to be now c, this c right here, and this d right here. The lower y and the upper y, right? That's going to be. And obviously with respect to dy. So that's basically what you're doing here. So let's go ahead and do the last problem. Find the area of the region in example 6 by integrating with respect to y. Example 6, that's just this one that we finished. So I'm gonna, instead of wasting more time, thanks for technology, I'm going to just basically copy all this again. Okay, so I'm gonna leave this here so that you see it's the same thing. I'm also gonna bring in the graph. Okay, so that way I don't have to redo it again. There. Okay, what else do I need from over there? I think that's it. So, and you would have to, yeah, just that. That's all I want. I don't want to confuse you more. So that's all we need. This, let me just finish it here. Okay, so it's the same scenario. Okay, but now it says that you're going to do everything with respect to y and not with respect to x. That's what the instruction is saying. Find the area of this with respect to y, integrating with respect to y. Keep in mind something, I'm going to rewrite it again. F is going to be the right hand curve or graph, right, whatever. This G is going to be the left hand curve. So be careful when you do f of y minus g of y. That is not changing the order of how you use the theorem. The theorem is still that. When you subtract this function on this side, let's say, minus the other one, okay, that's how you're going to do. It's never going to be something negative, okay? Because it's like when you're going, let's say, from the number 0 to the number 2. And so you're doing 2 minus 0, this one minus this one, and the answer is never going to be negative. It's always going to be something positive, right? So then that's always going to be this subtraction of the one on the right minus the one on the left. That's the reason you're doing it in that order. It's always going to give you to a positive area. So now imagine, on top of all this thing that I am writing, imagine that now you're talking about calculating the area based on rectangles that are going to be like this, horizontal rectangles, instead of vertical. So I need to think of, okay, so now the limits are not going to be to the side. So probably it was a good idea to graph it again, because now I need to show you the limits from top to bottom, probably. Yeah, let's do the graph again. So that was the old graph. And all I'm going to do is copy the points that I had already plotted for that before. Can I erase this? Yes, I can erase. Yeah, and I don't erase the rest. Perfect. So then this is going to be 1, 2, 3, 4, 1, 2, 1, 2, 1. Now we don't need anything there. So then here I had the point at 0. I had a point at 0, 0. I had a point at 1, 1. I had a point at 2. No, at 2, 4. 3, 4. 3 was 1. Did I have a point at 3 for the square root of x? For the square root of x? It was just for 2. Sorry. So for 2. And the only reason that I'm drawing it again is for you to not get confused and being able to see this from scratch, as you should do it when it says with respect to y instead of x, even though it's the same problem. Then it's bounded also by the x-axis, which we already know. This is basically y equals 0, or we had said before that this was going to be either y equals 0 or g of x equals 0. So, okay, we have this, and the other line that I'm missing is to plot points for the x minus 2. So I had 0, negative 2, 1, negative 1, 0, negative 2, 1, negative 1. I also had the point 2, 0. I also had the point, I think it's 3, 1, and 4, 2, yes. 3, 1, and 4, 2. And so my line was, and I'm going to do the line with this. Sorry, it wasn't starting there. It was starting here. So now I want to find the area, but the area of this region right here. All this region, but it says everything has to be written in terms of y. So okay. First thing, I already know that I'm gonna be looking at this instead of from left to right, from the bottom to the top. So what's going to be the way to find the points of intersection here? Well, now you're gonna be solving the equations for x and for y. So the right hand boundary, now your right and left are going to be functions, not the one below and the one above anymore. So solve for x, this equation, y equals x minus 2. If you solve it for x, all you do is move the 2, so you end up with y plus 2 is equals to x. Well, this equation is going to be f of y equals y plus 2. All I did is replace the x by f of y, so that you can relate this to this. Why am I choosing the right boundary? Because if you look at this from left to right, more to the right, we can see this is the right side of this enclosed region, only this line. The left is going to be this. It's going to be, yeah, the left. So it was left. Okay. The left hand boundary. It used to be y equals the square root of x, but now, and that looks like a y, you're gonna solve for y. So how? For x, I'm sorry. You're gonna raise to the second power this, you cancel the square root and the 2, you leave the x by itself, and that's your function written in terms of y. So not f, but y, g of y equals y squared. It's going to be your left hand boundary. What's going to be the lower limit? Remember, the lower limits are going to be to the sides now. Look at this picture. I'm sorry, from the bottom and at the top. So what's the bottom? What's the lowest that this area is bounded by at the bottom? By the number 0, which is represented by the x-axis, by this line located at 0. So this is going to be simply y equals 0. What's the upper limit? What's probably the point of intersection, and that's the highest it's going to reach? Well, you're going to have to find that. You're going to have to equal to each other the two equations. Y plus 2 equals y squared. This one equals to this one. Doesn't matter which one goes first. But no, I was going to take the square, but no. What you can do here, or you should do, is going to be send everything to one side. I'm going to send these two terms to the left side. Y squared minus y minus 2. And then use factorization. Y times y, 2 times 1 is 2, minus and plus. So then this is y minus 2 is equals to 0, y plus 1 is equals to 0. So this is y equals 2, this is y equals negative 1. Are these two really points of intersection between the two graphs? I don't know. At y equals 2, do they look like they're meeting? At y equals 2, yes. But at y equals, what was the other number? Negative 1. If they meet or they're not meeting, we're using the same problem that says find the area of the region in the first quadrant. So y equals negative 1 does not even play a role. Y, first of all, over here. Negative 1 does not even play a role anymore. This one. Because I just want to know the area here. So then, that means this is going to be a discarded answer because it's an extraneous solution. Okay. So then, that was a negative 1. Okay. So now I'm ready to set up my problem, my formula. So what I was telling you is that now you're doing, instead of, and that's the reason that I drew the whole thing again, instead of you doing vertical rectangles, now you're measuring this through horizontal rectangles. You're doing horizontal little rectangles, and then you're adding the areas of all this. But instead of you doing that, you're doing kind of a shortcut. So what's going to be the area? You can calculate the area in a single interval because everything fits in a single integral or interval. Everything fits from 0 all the way to the y value of the point of intersection, which is 4, 2, up to here. Okay, y equals 2 is going to be the upper limit, and then this is going to be the lower limit. So I'm going to write the formula so that you remember. This is going to be f of y minus g of y with respect to dy. So what's going to be my c and my d? Go to the picture here. What's c and what's d? I just gave them to you right now. They're going to be 0 right here and 2. What's going to be f of y? We had already worked on that before. F of y, it's going to be this one. Okay. Because that's the one on the right side, we said this line is more to the right compared to this curve. So then you're going to put y plus 2 minus the y squared. So probably the parenthesis was not even needed. dy. Okay, so now what we have left to do is do the evaluation of this. You don't have to break it into two intervals this time because, as I said, everything fits in there. You can leave it in this order, it doesn't matter. So this is the integration for this. So I just did the short version, right? Instead of writing plus 1 plus 1 plus 1 every time. You already saw me doing that several times. So now the integration is going to be y to the second over 2 plus 2y squared, 2y, I'm sorry, minus y to the third over 3, evaluated from 0 to 2. And then you're going to say, okay, so first you're going to say 2 squared over 2 plus 2 times 2 minus 2 to the third over 3 minus 0 squared over 2 plus 2 times 0 minus 0 to the third over 3. So that's going to be 2 squared is 4, divided by 2 is 2, plus 4. 2 to the third is 8, divided by 3 is a fraction, minus 8 thirds. All this side is going to be 0, so we kill it. So we don't even need the minus afterwards. You probably do not even need the parentheses anyway. You may put everything at this point on the calculator, or you may, I'm going to put the answer here, or you may do this step by step. You can do the 2 and the 4, that's going to be 6 minus 8 thirds, and now enter this into the calculator, or you could have entered everything at once. Minus 8 over 3 in parentheses. So the answer for this is going to be 10 thirds. And that would be the answer. Now, this is an alternative to do in a much, much faster way, because you don't have to break this down into two different intervals. You're doing horizontal rectangles or integrating with respect to y, and you see it is less work, honestly, than the other one. And my answer is the same as if I do the same problem but integrate it from left to right, or in terms of x's, because now I have different lower boundaries. One time was this equation, g of x equals 0, the x-axis, the other time was this line. And that's why I have to break it into two intervals, and everything is more work. But guess what the answer was at the end? It has to be the same, because you're calculating the area of the same region, but you're doing it into two parts, because you have to, because of the reason that you have two different lower boundaries. Here you only have, you have the same left boundary and the same right boundary. These are your values that are going to be your lower and upper limits, the 0 and the 2. So it becomes easier. So this lets you to think that in a problem, if you see that it's going to be easier doing everything with respect to y instead of with respect to x, because it's less work, and you want to do it that way, do it. But if not, do the x, because I know we're all used to doing everything with respect to x, and that's just another way. I'm going to show you a third way of doing the same problem, even in a much, much easier way. And for that, I'm going to open another slide. So it's the same problem, but done in a different way, and I know you're going to like this next one. So I'm not going to copy everything again, because it's the same problem, okay? So I'm going to do this in an algebraic form. Okay. What's going to be the algebraic form? I'm going to do the graph here. 1, 2, 3, 4. So then it's going to be 1, 2, 3, 4. This is going to be 1, 2. So then this is going to be right here. It's not a line, it's supposed to be a curve. Okay. For some reason I cannot do it. Something like that. You know, that's the curve that we had. It's not a line. Then the line came at 2 and up to meet here. So this is y equals the square root of x, and this was the line y equals x minus 2. So I want you to notice something. Now we're going to do this in a way easier form. Think of this as if you would close this. Sorry, because everything looks crooked and it's not supposed to be crooked. This is not an isosceles or something, okay? It's supposed to be this type of triangle where what's the distance here? 2. What's the distance from here to here, from the tallest part or the highest part? It's a 2. So you can do this through geometry, through the use of basic geometry and integration, obviously. So you're going to set your integral, your area for the integral, from 0 to 4. Why from 0 to 4? From this number 0 right here at the origin all the way to the number 4 over here. Okay, from 0 to 4. What's going to be the formula that I'm going to see? It's going to be, since I'm doing it from this side to this side, and I'm going to do all this thing and take away this piece, because I want to know the area of this that I'm going to color right now. I'm still looking for the same thing. I'm looking for the area of this piece. It's just that I'm going to find the area of this entire piece, including the triangle, but then I'm going to remove that triangle by using the formula for the area of a triangle. So much easier, you'll see. So then this is going to be, what is going to be my, let's say my boundary above. Obviously this is the square root of it. Okay, so I'm going to do, and what's going to be the boundary below? Shouldn't put this yet. It's still going to be what used to be before. The boundary before of all this, including the yellow triangle, it's going to be this, which is y equals 0 or g of x equals 0, because this at the same time is going to be f of x, right? The one above is f of x, the one below is g of x. So you do this one minus the one below, still going to be the same thing, and you're supposed to do the derivative of this. I'm going to find with this the area of the entire thing, but then I'm going to subtract to this one the area of this triangle. What's the formula for the area of a triangle? It's 1/2 times the base. I know the exact base. What's the height? I know the exact height right here. So this is 1/2 times the base times the height. And this is the area of a triangle, what I'm doing here. So then all I have to do is simplify this before actually doing the integration. Square root of x minus 0 is the square root of x. I'll do the integral with respect to x right now, or the antiderivative. Minus, what's going to be 1/2 times 2 times 2? You put that into your calculator, you do it on your own. It's 2, or minus 2. So in the next step, all I'm going to do is actually do the integral of this, but only the one that is a function, not the one that is a constant. It's a number. There's nothing to do there. Square root of x, but I should do the integral. What's the integral of square root of x? Well, you know it's x to the 1/2 plus 1 over 1/2 plus 1. You evaluate this from 0 to 4, and then all you're going to do is you're going to subtract 2 to that. So that's going to be x to the 3/2 over 3/2. From 0 to 4 minus 2 at the end. This is an easy one. So first you're going to say, no, simplify. So this is going to be 1 over 1. So 2 over 3 x to the 3/2 minus 2. So this is going to be, again, from 0 to 4 still. So here I'm going to do the evaluation of the upper boundary. 2/3 times 4 raised to the 3/2 minus 2/3 times 0 raised to the 3/2. Whatever I get, minus 2. This is going to be nothing. It's 0. 2/3 times the square root of 4 to the 3rd. We've done this several times already. I don't know why I put an equal sign. It's just a minus. Two-thirds. This is 64 minus 2. Easy peasy. So 2/3 times 8 minus 2. So first do the multiplication. 2 times 8 is 16. 16/3 minus 2. So what's 16/3 minus 2? If you put it on the calculator, you're going to get 10/3. we had it, no, we didn't have it there. 16/3 minus 2 10/3. That's the same answer as the two other ways that I've shown you how to find the area of this. Through basic geometry, but you're still doing integration, which is calculus. Through doing integration with respect to y in a single interval, where now your boundaries are going to be functions, and you always do f of x, f of y minus g of y, the one on the right minus the one on the left, and your lower limit, upper limit is going to be the lowest y and the highest y that it reaches that area. Or the regular way, that one that I know that we are more used to doing with the x's, everything with respect to x's, but this becomes lengthier because you have to cut it into 2 pieces. Okay, this concludes this section. Okay, and this concludes the entire calculus course. So if you have any questions, feel free to ask me next time in class, or send me an email, and I'll be glad to help you out. Okay, good luck on the final, and good luck in all your academic endeavors. It was my pleasure working with you.